what is this? Hey, by the way, look at.
Oh, 1871. So I told you it's a weapon from the old age, right?
Yeah. 1871. And still in use.
Still in use. Very practical then,
Yeah.
right? Tried and tested.
Yeah. So
this must be probably one of the oldest
one of the oldest
measure linear position
sensors.
sensors. Yeah.
It has got its own limitations, but it has got some benefits also.
Yeah.
I mean, the cost could be very low.
Right.
Easy to manufacture. I mean, it may not be a great one to manufacture, mass manufacture.
Right.
But if it's made in a small factory, it's kind of easy to manufacture. But for mass manufacturing, we may have to look at others.
Yes. I mean, this is probably very good for test circuits, right?
Yeah. So the wiper width that you mentioned, I have a better figure here. I was trying to draw something, it was not great. So this one, I mean, let's say I have taken a cross-sectional view of this. Cross-sectional view in the sense, I've taken something like this and I made a cut through the center.
Right. So the coils cannot go around.
Yes. So these are the faces of that coils.
Yes.
So that makes it clear, the width of the wiper should be at least,
wide enough to.
Yeah, wide enough to, I mean, before I leave one turn, I should make a contact with the other turn.
Yeah. And this wiper, what is it made of? Do you know?
It could be
something conducting. Right?
Yeah. It could be, I mean, copper. I mean, I have also seen some carbon kind of material.
Right.
Because one thing, it should be hard enough, but at the same time, it should not introduce a lot of friction.
Right. Yes. Otherwise, it might get stuck at certain points.
Yeah. So actually, that's very important point, no? We discussed in the previous class also, like we are trying to measure something, that measurement device should not alter the measurement itself.
Yes. Right? That's a big problem, right?
Yeah. So let's say, I mean, my hand is freely moving and you have introduced an instrument to measure the movement of the hand.
Right.
If that instrument stops my hand movements, then you have killed the...
Yes. And then exactly. Then your principal objective is met.
Objective is to measure, but you have stopped the...
Exactly. Right.
So the purpose is gone.
Yeah.
So that way, this friction is a problem. So the friction, I mean, now there is a friction between the wiper and the wire wound structure.
Yeah.
Whatever the input I am giving here, the movement has to provide that energy.
Yes.
It is taken from the measurement.
Right.
Which I don't like, but that's
how it is.
Yeah.
But also, nice point here is, because you mentioned friction, right? Now, if those coils are close together, I think there will be less friction somehow.
Yes.
Right? Because now it's going to bumps. So maybe there is also some technical details regarding that.
So we were talking about the output.
Yes.
So initially I've drawn some output versus displacement.
Yeah.
Something like this.
Yes.
I mean, this is the travel or the distance moved by the moving member or whatever we say. Movable member. And then I would prefer to get an output like this.
Yeah, we always like linear output.
Yeah. So that is easy for calculation.
Yes.
Like we said, at the center you have 5 volt, you move 2.5 centimeter more, you have 7.5 volt.
Exactly. Nice gradient.
Yeah. For the user, it's easy.
Yes.
So will I get something like this?
I'm not sure anymore because based on the discussions we've had regarding the winders, the coils, I'm thinking maybe we might not get a smooth, maybe not that smooth.
Correct. Because it looks like, I mean, let's say I am in this terminal, I have voltage.
Yeah.
Once I am at this turn, I will have a jump from there.
A little bit of a jump. Yeah.
So this means I make it something like this.
That is possible. But maybe not as pronounced as that. Again, depending on how far the coils are, I think, right?
Yeah.
But yes, I think in my mind, this is how I
like you said, if you use many number of turns, then this can become smoother.
Yeah.
That's your point.
Yeah.
Anyway, out of curiosity, I've done some measurements. So,
You tested one?
Yeah, I tested. I mean, I applied this Vs here, the same resistance AB, and then I measured that voltage across the movable member and B. I think compared to our previous diagram, A and B's are, I will replace. So this is B compared to our previous diagram. And I think this was A. And let's say this is C. Right. I can use a multimeter to measure.
Yes.
And I have done this displacement like this, recorded everything very carefully.
Okay.
I got something like this.
Oh.
I thought I'm not good at experiments. Again, everything properly connected. I tried once again coming like this.
So it's a little bit like this?
It is somewhat like this.
But also it's not...
yeah, but in between I see other stems.
Yeah, exactly.
And also you see that jump is increasing, that height of that is increasing as I travel more.
Yes, I can see that. Yes. I didn't notice it before.
Yeah.
Yes.
Somehow it's not.
But how is that possible?
I don't know. This is...
and it's the same when you go the other way around too?
Yeah, it was. I tried 3-4 times.
It's identical.
I changed the instrument.
So if you go the other way, then this will decrease.
Yeah.
The jump will decrease.
Yeah. The characteristic is same. Whether I come from here to here or here to go this side, I get the same output versus or travel versus output.
I see. Okay. So that doesn't make a difference.
That doesn't make a difference. So first thing is, I mean, something like this, I would have been okay, man, this is the output, fine. But here, these things were confusing. So I had to refer to somebody else.
Yeah, that is a bit confusing. So does that also mean if you increase the length, this would just get worse and worse and worse?
Yeah, finally, I think the last jump will be as high.
Yeah, this will just be a big jump. Yes.
So how to solve, I mean, how to understand this better?
Yeah, I'm a little bit confused.
Yeah. In fact, this so far what we discussed is the linear position sensor. Yeah. We can also realize this for a rotary one.
I mean, it depends if
it is wound on a circular structure.
If it's going around.
Correct. Like this.
Yes.
So I have the winding here, as you can see. Sorry. And the wiper arrangement. This part is the wiper.
Yeah.
So in fact, I tried on that also. Whether the characteristic is length, it's the same.
It's the same?
Yeah. So we need to spend some time on this to understand more.
Yeah, because if it's like this, it's still okay.
Correct.
Somehow, right?
Correct. But so because we want a very predictable output.
Exactly.
Now, if it is like this, we wanted to know why is it so?
Yes. I mean, okay, so it's still somehow linear, but these little ones, little jumps are increasing. Right, so that's a problem.
That is in the engineering. I mean, we don't leave things just like that.
And this is our primary source of measuring.
Correct. So, I made a better drawing to understand this. Let's name each turn. I mean, let's say first turn is 0, 0, 1, 2, up to, there are n turns.
Okay.
So, now if you apply a voltage, Vs, I mean, earlier I said Vs by L, or unit.
Less a wire.
Yeah. I can also now say, because this is wound uniformly,
yes,
I can also say some Vs by N.
Yes.
Each turn we have this much voltage.
Right.
So if I am at 0th turn, I have 0 volt. Because that's connected to ground.
Yes.
Let's assume that this is connected to ground. If I am in the first turn, I will have Vs by N. Second turn, if I am correctly touching, I will have 2 Vs by N.
Yes.
And so on.
Yes.
Now we will think, why is this small jump coming in between.
Okay.
See, you had a point about the width of the wiper.
Yes.
So assume the width of the wiper, or look at this drawing. What I have is, it's touching 2 turns now.
Yes.
So if that's the condition,
Mhm.
what is the total number of turns now? Is it n, or is it something less than n? Because you're shorted 1 turn.
Yes.
So it will be n minus 1.
Because now you cannot say for sure 1, 2, 3 like this.
Yeah,
Because you're touching both.
correct. I mean, the wiper can be even here, but you have shorted 2 turns.
Yes.
So the turn in between has no effect.
Yes. Yes.
Correct.
So you reduced.
Yeah, I reduced 1 turn. I mean, it's difficult to draw here. So I think earlier we tried, no? So if I touch these 2, then this portion has no effect, no?
Yes. Because you shorted it.
So basically 1 turn less, then that happens.
Okay.
So when you make that make before break contact,
Mhm.
you are shorting 1 turn. So total number of turns is reduced.
Okay.
So that means your actual number of turns at that time is n minus 1. So the volt per turn will be Vs by n minus 1,
Ah. Okay.
which is higher than, of course, Vs by n.
Yes. Which is this little jump you see.
Yeah. So that's what. When you are actually at turn 1, you will have Vs by n.
And it looks nice.
Looks nice.
Yeah.
When you make a contact between 1 and 2, you see a jump there.
Yes.
So that jump is due to this, because you have reduced 1 turn.
And that means you're shorting now.
Correct.
Right.
Now, how to get the height of that? Maybe we will mark it as delta V min.
Okay.
How will I get that?
But then you have that.
Hmm.
What happens now when you go to the next one?
Next one?
Does it repeat the...
Yeah, so wherever I am, so let's say if I am here, then also I am shorting 1 turn.
Correct. But then I also see from here, these jumps, the V min that you're talking about
Is increasing.
is increasing, right?
Yeah.
And also this V major.
Oh.
Does V major remain the same?
V major is reducing. So
Also reducing.
yeah, so the V major here is this.
Exactly.
At the end, V major is only this much.
So now we have both.
Yeah.
So once reducing, V major is reducing.
Yeah.
V minimum is increasing.
Correct.
What's the relationship between
Yeah.
them?
So first thing what I want is,
V minimum.
what is this delta V min? So we know this. It's Vs by n minus 1 now. So that means Vs by n minus 1 minus Vs by n. I was expecting Vs by n, but there is Vs by n minus 1 volt now.
Yeah.
So that difference will be delta V.
So that's the little jump you see.
That's the jump. Yes. Now your question, why the jump increases?
Yeah.
When I come here.
When you increase n,
Yeah.
your jump increases.
Yeah. So let's say you are here now.
Mhm.
Means
Between 3 and 2.
yeah. Or 2 and 3 you're short.
2 and 3, yes.
So that means you have 2 turns before your contact point, wherever wiper is
Yes.
standing there now.
Yes. First, took second one, and
Yes.
then the third one.
Yeah.
So 2.
So actually, every turn has got Vs by n minus 1.
Correct.
So when you have 2 turns,
2 times.
there will be 2 times Vs by n minus 1. Right? So 2 times Vs by n minus 1 what I was expecting there is 2 times Vs by N. Yes. So what you see is the delta V min when you moved further, just increased. Yes. Or I can say, let's say this is X displacement. Okay. Here we are mentioning it as 0, 1, 2, 3, etc. Yes. So I can represent in terms of X also. So it is X into Vs by N minus 1 minus Vs by N. Correct. So what it indicates is as X increases, your delta V min will increase. So that is why this step is increasing. Yes. Anyway, volt per turn, when it is not, when this short is not there, is Vs by N.
Right. Yeah, that's understandable.
Yeah. So if delta V min is increasing, obviously delta V major will decrease. But because the total height remains same.
Yes, but here it's increasing by a factor of X.
Yeah.
Correct?
Yeah.
But then here, it keeps on, the actual step keeps on increasing.
No. So X and the steps, they are the same.
They are the same, yes.
It's, here we represented in terms of number of turns. It could be in millimeter or centimeter, depending on the range of your sensor.
Right.
I think I have this written in a better format. So delta V min is this Vs by N minus 1. Because you have made a short, 1 turn left now.
Yeah.
So there is an increase in voltage. What is expected is Vs by N. So that difference is delta V min. Delta V major is, the total voltage per turn is Vs by N.
Yeah.
You already made a jump of delta V min.
Yeah.
So the rest is delta V major, which is this.
Yeah.
So I think that.
Okay, that's understood.
Yeah.
When that increase, that has to decrease.
Correct. Yeah. Correct. Now I see there is some term called exclusion. What is that? Applied voltage we earlier mentioned. Vs. Fine. But this resolution.
Resolution is normally
the cell phone camera says so much of resolution.
Maybe the smallest step size or the smallest measurement we can measure. Over between two values.
So the smallest quantity that you can resolve.
Yes, I guess.
So why I have L by N here? In this case. So what we are saying is you have a total length of L.
Yes.
And you have put N number of turns.
Yeah. Because your L can be, divided into, 1 millimeter or 1 centimeter.
So like you said, I have only N number of turns.
Yes.
I can make contact with 1 turn, 2nd turn, 3rd turn, or 1st turn, 2nd turn, 3rd turn, like that.
Yes.
There is nothing in between.
No.
Correct?
Yes.
So I cannot resolve something smaller than that. Correct. So that decides the resolution, or that is the resolution.
We are limited by that.
Yeah.
Yes.
Whatever you do, you cannot get a smaller quantity resolved from this.
Yes.
This specific elements. Yeah.
Yes. Now, can you increase the number of turns? Yes.
Yeah. So if you can increase the number of turns, the resolution will increase. Yeah. That's what it says.
Right.
I can resolve smaller and smaller quantities.
Right. So how would that affect the graph? Now, let's say if this is closer.
Yeah. So suppose if let's say N, I made it double.
Yeah.
Then obviously this step will become half the height.
Exactly. Right.
So the step size will reduce.
So that means
it will become more smoother.
If you do it infinitely,
then
will it become like this?
Then it will come close to this.
Yes.
Right. Yeah.
Correct.
So it is a question of what is, how much cost you want.
Yes, and also the practicalities, right, of making something like
correct.
That. You cannot go as small as possible,
correct,
right?
Correct. Yeah. Now, suppose if I want something like this, is there a way?
We'll have to overcome.
Yeah, obviously this wire wound
mechanism will not work.
will not
because, as you said, you can increase n.
Yeah,
you can get close to this.
correct.
But I don't think we'll ever get this.
Yes.
Right. So the structure will have to be changed.
It has to be something else.
Yeah, has to be something else.
I was searching for it. I got a figure. Okay, I think this we explained.
Yes. Did we?
Yeah, this we explained. I was mentioning that it's x times.
Correct.
The delta V min is x times Vs by n minus 1 minus Vs by n.
Yes.
This we discussed already.
Right.
Delta V major will be Vs by n minus that.
Mm-hmm.
Right. Then we were discussing about the smoother one. So this is the figure I got from internet.
Okay.
It gives it doesn't give a random jump like, it's not random. It's very predictable jump.
Right.
Now we understood.
Yes.
Usually I was thinking it's something wrong with my experiment.
Right.
Then I thought something wrong with the sensor itself.
But it's clear now.
It's clear scientifically why it is so. So on that basis, what is this? They say you can get, wire wound type you forget if you want smooth output. They use a continuous track potentiometer. They say use a conductive plastic.
So what I can see here is a continuous track.
Yeah. So we can see a track like this.
Yeah.
Right.
Mm-hmm.
My drawing is not good, but that is one track. Then there is another track here. Then there is some connections here.
Okay. But no coils.
No coils.
Like a planar coil.
Yeah.
This is a planar coil.
Yeah. So it's difficult to maybe explain in this circular fashion. Maybe I can explain in a linear fashion. If it's a linear displacement sensor, right, instead of a rotary, then I would be, let's say the outer structure, I take out and keep it like this.
You mean the green part?
No. This one.
The black one.
The outer black one.
Yeah.
So let's say this is terminal A and this is terminal B. I have A and B here.
Okay.
So earlier we said, if you can give a voltage here, this will get distributed equally, etc.
Yeah.
Let's say this Vs is given.
Yeah.
Now, the inner one, let's say I have one more strip here. Then, or this is our ground. So let's say I take output across this. C, and this is B. Let's say VBC or VCB.
Okay.
Now it will be nothing because there is no connection between these two.
Yes.
So let's say there is a wiper connecting these two.
Okay.
On top of this. So the terminal, the voltage of this C or this strip will be the potential at this point.
Correct.
That's what we want.
Yes.
So it's, earlier we used to connect from that wiper directly.
Yes.
Now they have introduced one more circular strip and make a contact like this. And as I move, this one will move.
Which means this will move.
Yeah. So, I mean, let's say if it's earlier we were mentioning 2.5, etc. So let's say 25% movement, it will be somewhere here. So I get 2.5 volt.
Right.
If I'm at center and Vs is 10 volt, I'll get 5 volt output.
Right. Right.
Like we mentioned.
So the wiper is now connected to both.
Yeah. Now wiper is connected to both of them. The inner one here is only to carry that voltage to the outside world. Right. The outer one is used as a voltage divider.
Right.
So voltage is divided uniformly across this. The wiper passes that information from this to this, and I measure from here. Same thing here.
So you have it in a circular direction here because you can make it long.
Yeah.
Is that the reason? Yes.
Or
what is the advantage of this
circular shape? It is only to realize a circular or angular sensor.
But also if you go this way, you'll have a very long.
Yeah, actually this is also available. This type of
the long one.
Linear position sensor is also available.
Right.
So only thing is the way in which the resistive element is introduced now is different. Earlier it was a wire wound one.
Yeah.
Here they use this conductive plastic, so which is very smooth and the resistivity is large.
Right.
Much larger compared to the just the nichrome or the wire wound that we use.
Right.
There, like you said, we could have used thin wire and get large resistance.
Right.
Here, the wire is not thin, but the cross-section area of this coating is very thin.
Very thin.
Very thin. But it is wider so that you can make good contact.
So your resistance is high.
Resistance is high. You don't have problem in this contact area. Contact area is good. Also, there is no wire wound work here. Yes. So this can be mass manufactured.
But then this kind of track, if you keep going over and over again, will it get somehow scratched or
maybe?
Or is it quite robust?
So it may get peeled off after some time. So,
right.
But I think that they are sold. I've seen it can move million times or something.
Yeah. Right. So that's a solution then to overcome Vmax and Vmin. That
so you get a
function
very very smooth output characters.
Did you try in the lab?
Yeah. Of course, we measured and it's very
nice.
Yeah. So just to conclude, so we had introduced some terms in our discussion. One thing is range.
Yes.
So I mentioned something called L.
Yes.
Yeah. Usually small letter we will not use for full, the range.
Right.
Usually people use capital letter.
Right.
But doesn't matter. I think we define it as so range means what's in the case of a displacement sensor, it's the maximum distance or maximum displacement it can measure.
Right.
In the case of a pressure sensor, it will be the pressure that it can withstand and measure.
Correct.
So I've seen instruments or sensors in the range of millimeter to meter range. The wire wound range. Right. Also, rotary one, we have shown 360 degree.
Yes.
But there are structures that can give you more turns. More than 360.
So this 60 turns is rotary. What are you referring to? Are the coil-based one?
Coil-based one.
Coil-based one. Yeah. Okay.
Yeah, there are some terms called linearity.
What is that?
I don't know.
I know FS is full scale.
FS is full scale. Yeah.
So what does that mean then? Full scale means?
So what it says is 0.000 202 to 0.01% of full scale.
Yeah.
So there in our example we said 10 volt is a full scale.
Yes.
Maximum voltage is that.
Right.
So full scale is that.
Right.
And we were looking for a characteristic like this.
Yes.
Correct?
Yes.
Probably what it says is, you were mentioning more number of turns and so on. So the step size will come down, but there can be the output need not be a very straight line like that. I have exaggerated a little bit. It may deviate little bit from the linear characteristics. Right. So that introduces
some non-linearity.
We will discuss this in detail more. So you can get, very good linear characteristic from this sensor.
But 0.002% is very
good. Yeah.
Right?
Oh, very good. Yeah.
Even 0.1.
Yeah. Right? Maximum frequency. Because the wiper, maximum the displacement, it cannot be 100 hertz. By the time it will go into pieces per word. Correct? Yeah. So typically, low frequency, some various range. Yeah. Okay. Yeah.
But then again, to measure linear displacement, you probably don't need very high frequency, right?
Yeah. If it is something moving very fast, then we may have to look for different ways of measuring. Exactly.
Because now we are looking at specifically potentiometer.
How to use a resistive element for displacement measurement. Right. That's the question that we are discussing.
Yes.
Right? Life aspect, it's
quite clear.
Right? Yeah, this I think we discussed.
This is...
The patent was in some, still people are using. One thing is cost effective, simple, reliable, and you don't need much electronics to measure from this also, right? Because you just apply the voltage, measure this.
You measured it from a multimeter, right?
Yeah, that's it.
Yeah. And I think because of the last two, that's why it's widely used.
Right? Yeah, it's still...
Anyone can use it.
Yeah. Nice. So, this is one of the sensors.
Yeah.
Interesting, no?
Very. I think...
we started with something, a weapon.
A weapon. And
now it's a weapon for an engineer.
And also, simple electronics, right?
Correct.
Very basic things, but, it can do some nice things.